I want first to thank the organizers to invite me here. I will try to talk about attosecond science a little bit from an atomic physics point of view, which is my background. This is the group in Lund working on these processes. Per Johnsson, Thomas Remetter, Erik Gustafsson, Marco Swoboda are PhD students. Per is very soon finishing in 1 month from now. Thierry Ruchon, postdoc. Katalin Varju is former postdoc. She's now back in Szeged in Hungary. Mauritsson is assistant professor and is here. This is him. And next week he will talk about attosecond pulses using a two-color driving field. So I really encourage you to come to his lecture and to stay till next week. And I will just highlight some of these results. Now we benefit from the infrastructure of the Lund high-power laser facility with 2 laser engineers, and it's headed by Klaus-Göran Wallström and Sune Sandberg. Now we have a long-standing collaboration with the group at Louisiana State University, Ken Schaefer and Mette Gårde. I'm very happy with that, and we are very actively collaborating with European groups. There is a very active European research in this field, as you know, driven by European programs within the Laser Lab Europe and within the networks, the Marie Curie Actions, and now it's Extra Network, which is coordinated by Mark Bracking, and this is really helped this research very much. And now I just here cite 2 last collaboration we have been doing with the group of Mark Bracking and with the Laboratoire d'Optique Appliquée. I start this by what I'm going to talk about is really ionization of atoms in the extreme ultraviolet range. And just to put that into perspective, this is really one of the first results obtained for almost 40 years ago. This is really one of the first synchrotron radiation results. And this is a really beautiful spectrum. This is ionization cross-section of argon in 30 eV range, and this is really what I'm going to talk about. 30 eV, about a few eV bandwidths, but really differently. And you see these beautiful structures with the doubly excited auto-ionizing states. Now, my reaction to Tony's email was a bit different from Mark. I said, oh, what I'm going to do? And I said, oh, great, I'm going to do that like I'm teaching. So I'm trying to ask you questions, and I hope you have to respond me. But I just first like to maybe say 3 more philosophical questions, and then during the talk I will ask more specific questions, and there you have to answer me, I hope. So now a few questions, first of all. Can we look at that, photoionization of atoms in the extreme ultraviolet range, not in the frequency domain as this dot, but in the time domain? This is the obvious thing. And attosecond time scale is the right time scale, as you know. Can we learn something? And this I have very often the question in Sweden, because Sweden is a country where spectroscopy has been developed quite a lot. I mean, this is really old-fashioned spectroscopy. Rydberg was professor in Lund. So I'm facing Rydberg every time I'm teaching. And you have people like Edlen, Sigban, and so this is part of the culture, and people ask me, well, can you learn something? I think this has been discussed at the conference. The answer is yes. Second question, maybe less obvious. Can we go from amplitude to phase determination? This plot is really here we measure the cross-section. This is the intensity, because quantum mechanics tell us that what we measure is probabilities. But okay, can we try to think a bit atomic physics, not measuring simply intensities, even differential cross-section, but really phases? And this I will illustrate in my talk. Maybe third question, which became clearer to me only recently, actually. can we go from measurements, really measurements of the atom properties, to control? And it seems to me, this is just, I'm just making philosophy here, not science, but it seems to me that, 20 years ago, atomic physicists learned to control the external degrees of freedom of atoms and cool atoms, and this has led to fantastic applications. Now it seems to me that we are learning a little bit how to control the internal degrees of freedom of atoms. So I think attoscience is not, what I want to say here is that attosecond pulses, this is not only an ultra-fast camera, and it's really much more to it. And maybe this is the way to control electronic properties. Okay, what tool do we have? The first tool is this returning electron wave packet. It has been discussed at this conference. This is a very nice tool. It's relatively easy experimentally. Very nice application, tomography, structural dynamics. We have talks in this conference about that, and very beautiful work from the group of Murnane Captain. Second tool, single attosecond pulses, which has been pioneered by Ferencross and co-workers, first in Vienna and then in Garching, and again with beginning application in atomic physics. It's a very nice tool, very technologically challenging. This is not very easy to have single attosecond pulses. You need state-of-the-art laser systems. Now, third tool, it's a little bit in between. It's not so easy that just using the returning wave packet, but maybe we don't have as clean tool as the single attosecond pulse. Trains of attosecond pulse, and maybe I just mention tool 3'. This is proposition. This is using trains of attosecond pulses with only 1 pulse per cycle, which is actually quite similar to having only single attosecond pulse. This will be presented by Johan next week. So this is the outline of the talk. First, I'd like to do a little bit of attosecond technology. And the tool we have chosen in Lund is the third tool to make trains of attosecond pulse and to use them for application. So I will tell you how we make these trains. And actually, our attosecond tool is not a train. It's not a single pulse. It's really a combination of the trains synchronized with the infrared field. If you have only 1 attosecond pulse, you only have broadband radiation. You need to have 2 attosecond pulse with a variable delay between them to be able to do a correlation or pump probe. Alternatively, and this is what most people are doing in this field, you can correlate this pulse with actually the oscillation of the infrared field, and which is what we are doing. Then I will talk about 2 applications that we have developed. One is electron wave packet interferometry. This is just out in Nature Physics. We even have the cover. And then a more recent work about ionization dynamics. Now, got a reflection from Phil Buxbaum here at this conference that attoscience is a very strange science where people start discussing how the machine is working. No, they're not discussing science. They just say, "Oh, should we put some oil in the machine?" This kind of things. And that is true. I think the reason, first of all, it's a very fascinating machine, and we still don't understand everything about it. And second, I think this machine is very much what we can do with that is very much determining what we can do with the machine, and we have to learn actually how to use it. So it's really intricate. Now, how do we generate our attosecond pulse trains? Well, we generate harmonics using a kind of standard laser system, titanium sapphire, not phase stabilized, 1 kHz, 2 millijoules, 35 femtosecond pulses. And we focus it into a gas cell with some rare gas at a pressure of a few tenths of millibar. Now, to understand how to produce attosecond pulse train, from this high order harmonic generation. I need to do a little bit of physics of high order harmonics. I will not do much because I think this audience know everything about it. This is the Schrödinger cats that Ken Schaffer talked about. Who doesn't know this picture? Raise your hand. Okay, good. And this is actually a very nice picture from the work of Pukov and co-workers, showing the harmonic emission from a few cycle laser pulse as a function of time. And here you see very nicely the contribution of the first trajectory, the short trajectory, and the long trajectory. And this is the next cycle and the next cycle. You see a little bit of more complicated stuff. This is longer trajectories. And this is, well, you also see here a rather strong low order harmonic emission. This gives you the recipes to make this attosecond pulse. First, if you want to make a single attosecond pulse, what you can do is select the high energy part. This is the approach of the Vienna group. And of course, tells you immediately that to do that, you need a phase stabilized laser system. There need to be a difference between the response from this cycle to that cycle. Alternatively, there is another technique which actually selects not an energy region but the time region using the polarization gauging technique. And this will be presented tomorrow by Eric Mevel. And it has been beautifully applied in a collaboration between Bordeaux group and the Milan group. Now, we do not have a few cycle laser pulse and we not stabilize, so let's make trains. Here's a recipe to make trains. You still have to select a certain bandwidth, okay, because you don't want this low order harmonics. You only want this certain bandwidth here. What else? Well, we only want to have one pulse per cycle, per half cycle, sorry. Okay, so somehow we have to get rid of the contribution of this second trajectory here, otherwise it's complicated. So we have to get rid of the second trajectory. And then if you want to have short pulses, then you want to compensate for the chirp of the harmonic emission that you can see here. This is not vertical line, it's increasing. So you want to make this straight to have very short pulse. You want to have all the harmonics at the same time. Now here's the first question to you, and I want some feedback here. Why can't we make a train with the second trajectory?
That's where all the energy is. That's where all the intensity is. It's gone away.
Yes? I tell you, I don't know the answer. I'm very intrigued by that. I'm fascinated by this question. Why can't we make trains with the second trajectory? It's very strong. You see it? If you yeah. Yes. I mean, we can. Okay, let me discuss this question a little more. This is actually a picture showing you harmonics as a function of this is the spatial profile of the 25th harmonic in Oregon. This is a result obtained actually. I have a small group. This Olivier Guibault is a postdoc and 2 undergraduates, and we're trying to optimize harmonics for seeding X-ray lasers or seeding free electron lasers. And so to do that, we like to tune the wavelengths of the harmonics. So let's chirp the driving field, and what we see they're moving, yes, but they are splitting. And this is, we believe this is the second trajectory and this is the first trajectory. Both of them are very strong. The divergence is not as different as one usually say, okay, because this is not too far from the cutoff. They are very strong, and I'm really puzzled by this. Why can't we really use this second trajectory? more. Yes. Yeah. Yeah. That's a very good point. See, I get some answers here. Yes. That's okay if I have some discussion on that.
We've made a comparison for the attosecond pulse productions in xenon, argon and krypton as harmonic generation gas. And what we've seen is that for argon and krypton the timing of the pulse was more or less where you expected it, whereas for xenon it was about a quarter period off. And this could be a difference in the ionization dynamics. It also could be the other trajectory.
Yeah. Well, that's a very good point. Okay, let me continue. Okay, then we have the recipes to make an attosecond pulse train. Generate harmonics, we have to get rid of the fundamental and do some spectral filtering, and then we have to compress the pulses. And this we do by using combination of a hard aperture and a metallic filter. So the hard aperture is actually the thing that we believe make the second trajectory disappear, okay, because it's more divergent. And the metallic filter allows us to control the amplitude of our attosecond or of the spectral amplitude. So it gives a low energy turn on, and then the other side is actually determined by the cutoff of the high order emission. The metallic filter not only allows us to spectral filter our attosecond pulse train, but also allow us to compensate for the chirp of the harmonic emission. It has a negative group velocity dispersion that compensates for the positive chirp. And this is the first results we obtain in argon using aluminum filter, different thicknesses, and you see how the phase of the harmonic emission can be controlled by using the appropriate thickness of the filter. And this is the reconstructed pulse, and the best results is in red. We got 170 attosecond, to be compared to the Fourier transform limit of 150. And these are actually very short pulse of only 1.2 optical cycles, centered at 30 eV. We tried to do that recently using neon instead, and zirconium filter, and this is a very recent result showing you here. This is the spectrum that we can filter using this zirconium filter. You see there are about 10, even more harmonics, and however it was more difficult to get the phase control so far. We are going to try to use a slightly thicker filter here to try to flatten this phase, but here we get about 130 attosecond. This is kind of a summary of what we have, what we can use to do attosecond science, using different gases to generate the harmonics, xenon, argon, neon, and different filters, aluminum here, and we actually try also silicon and zirconium. This is what, so this is different attosecond pulses, centered at 20 eV, 30 eV, and 78 eV. This is the corresponding pulse duration that we have measured. You can compare here with the Fourier transform limit. It tells you how well we can control this phase. And we also have investigated another technique, which is the use of a broadband chirp mirror. It is working, but the reflectivity of this mirror so far is really low. It's really too low. So the techniques of using metallic filter is actually working better. So I think, I hope the X-ray optics people will work more on these things and increase the reflectivity. Now, last thing I want to say about these trains is, well, we have worked quite a lot about the femtosecond structure of this train, how the pulse lengths vary during the train. And I'm not going to discuss that here. I'll just refer to this paper if you want to know more about that. Now, roughly speaking, we have a train of we have a spectrum of a few harmonics. These are only odd harmonics. They are separated by twice the laser frequency. In the time domain, this is a succession of pulses, quite short, separated by half the laser cycle, and they have a phase flip of pi between consecutive pulses. This will be important later in this talk. Now, if you can generate not only odd harmonics, but odd and even harmonics, then, if you do it right, you can get a train of pulses, now this time separated by a laser cycle, and with no phase flip between consecutive pulses. So these are actually phase-stabilized trains of attosecond pulses. And we believe that we have done this experiment. This is in a very recent PhysRev letter, and using combination of fundamental and second harmonic to break the inversion symmetry and produce this kind of spectrum. And this will be discussed by Johan next week. Now, to conclude on this attosecond technology part, let me say a few words about the characterization of this pulse. How do we do that? And actually, how do we have this train of pulse synchronized with an infrared field? This is our experimental setup. It is a Mach-Zehnder interferometer that actually looks very much like a Mach-Zehnder interferometer with the structure here. We split the infrared beam here. We generate harmonics here and attosecond pulses here, and then we recombine the infrared pulse on this mirror, which has a hole in it. And then we focus the two beams in the sensitive region of an electron spectrometer. Now, the characterization technique that we use to measure these pulses is the rabbit technique, very nice technique that was presented actually in the first paper on attosecond pulses. And it's a weak field technique, perturbation theory, where what you look at is, so this is a rabbit trace that we have, showing you the electron spectra as a function of delay between the XUV pulse and the infrared pulse. You recognize here the harmonic peaks, and then in between you have the sideband peaks corresponding to additional absorption of photon or emission of photon. And the oscillation of the sideband that you see very clearly here depends on the phase difference between consecutive harmonics, and from that we can recover really the spectral phase of the attosecond pulse over the whole spectrum. Now, the second technique that is used in this field is the so-called AC streak camera technique, which was proposed by Paul Corkum and his group and applied very beautifully by the Vienna group. And this is actually a so-called streaking trace obtained in Vienna. This has been explained in this conference, so I'm not going to say very much more about it. The physics is that when the electron is born at a minima or maxima of the vector potential, so this red curve here is the vector potential, then this is where you have the maximum momentum transfer from the field to the electron, and this is where you get the increase or decrease in energy here. So this leads to this streaking trace, and from the sharpness of this trace you can recover the pulse duration. Now, if you use instead of a single pulse, if you use a train of pulse, what do you see? Well, you see something like that. You see, first of all, you see interferences here. This is really due to the repetition of the process every cycle. And then in addition, you see twice as many oscillation of the electron energy here, which is simply due to the fact that now I have two electrons interacting. I have one electron interacting with the lower part of the vector potential and one interacting with the upper part of the vector potential at each delay. Now, if you do that with only one pulse per cycle, as Johan will show, then you recover, of course, You still have the interference stripe. You have again one pulse. You recover the 1 pulse per cycle structure. So this is actually very much, this is very close to this streaking trace here. Now, to finish that part, I will just flash here a result that very recent obtained by the Milano group. This is using this polarization gating technique. So they have only one attosecond pulse, and this is again the streaking trace. You see it's a beautiful streaking trace. This is at 30 eV energy. And what you see here, and this is the recovered pulse duration. And if they use compress the pulse a little bit using 300 nanometer aluminum filter, they can even get rid of the chirp that you see here on this trace. And this is the trace obtained, and this is the result, 130 attosecond pulse. So this is a very brand new result, which I'm just showing to you. Now let me go to the second part of this talk, which is about application. And the first thing I would like to tell you is about electron wave packet interferometry. And I need some tool here, which this. Okay. Let me explain the idea by using a very simple system, which is helium ionized by a 37 eV photon with a bandwidth of 15 eV. This is 160 attosecond pulse. The polarization of the field, the XUV and the infrared field, is in the vertical direction. And I am switched from electron spectra to a momentum distribution. So this is the momentum distribution, Px, Py. This is the intensity distribution. And what you recognize here is the simple dipole emission that you have in single photon ionization, proportional to cosine square theta, where theta is the direction between the momentum and the polarization of the field. Now, what happens when you expose your atom to an infrared field? If this infrared field, if the attosecond pulse here coincide with the zero of the vector potential, basically nothing happens. I show it again. This is without infrared field. This is with infrared field. Nothing happened. And here comes my second question. And okay, I'll do that again. Now, let me say one more thing. Now, if I superpose this attosecond pulse now to a minimum of the vector potential, what happens, as you know, the electron gets some extra momentum from the field, the distribution just moves up. It moves up, but it doesn't change very much. You see, this is very important for the argumentation I'm going to make. It just moves. It gets some extra momentum. It just moves. So here's my question: is it strong or weak field? And let me tell you the problem. If I think in energy, okay, this is the regime of the streaking, which means that the electron does absorb several photons of the infrared field. So if I just look at the electron spectra, you really get absorption of many infrared photons. So you would like to think of it as a strong field thing. But now if you go to momentum space, what you have is just move. And I would like to say this is a weak field thing. I'm not perturbing this momentum distribution. I'm just moving it. Please answer me. Ken. Yeah. Yeah, but you see my point. I still won't like to say I'm just manipulating my momentum distribution, and I want to recover from measurements now the initial momentum distribution.
You could treat this classically.
Yeah.
Classical field. And the question is, Can one experimentally observe evidence of infrared photons? I'm not sure we can.
Yes, you can. This is the yeah.
I think if the nucleus is still there, then it's a very strong field, because that wave function has simply no overlap with the initial wave function. And that would sort of be, at least to me, definition between perturbative and non-perturbative is the overlap with the initial state.
Oh, this is non-perturbative. That I completely agree. But my point is that and this is also the message that we want to transfer to other communities. I want to be able to say this is really, I'm just manipulating the electronic wave packet. I'm not slashing them around. Yes. Yeah. Yes.
I think that seems to be a sensible view. Surely what you're really interested in is the coupling from the bound state to the continuum, and that's not really changed by this additional dressing. I think you're arguing, and so the momentum distribution of the original wave packet has not changed.
Yeah.
And I would agree with you in that sense. It's a weak field, and it's partly, I guess, to do with the fact that the field is not changing very much the ground state of the system. I mean, it's weak from the point of view of stark shifts of the ground state or distortion of that wave function.
Yeah. I mean, just to put some numbers, this is 10 to 13 watts per square centimeter. Yeah.
Maybe it's just semantics. I mean, it's obviously a strong field, but I think in this experiment it's weak from the point of view that the infrared field does not induce a recollision, because that's what would actually change the wave packet, but that's not happening here. So from that point.
Okay, continue. Okay, now let's have two. Yes.
So, hello? No. From the point of view of what Mark just said, I mean, and I think you'll see this in Johan's talk, there's another parameter to consider weak versus strong when you've launched something into the continuum, and it is this ratio of the initial energy. So in this case, your 15 eV to twice the Ponner motive energy. And so in that sense, so if you look at that, you can make sort of another Keldysh type parameter. So you could take this, you could say gamma twiddle is the square root of that initial energy to 2 times the Ponner motive energy. And in that sense, here, you're at gamma much greater than 1. So it's a weak field in that sense, and that's exactly what Mark means, which is to say, the idea of whether it's weak or strong is, once I've launched the electron into the continuum, is the field strong enough to take an electron that's initially heading south and turn it north?
Yes.
And in this case, the answer is no. And so what that does is that guarantees you essentially no post-interaction. So then you're in this regime that I'm talking about, where weak and strong is only how far I'm moving the thing. And again, if you look in Volkov theory or the SFA, something that doesn't ever include any post-interaction, then this would only just, weak and strong is just a term for how long did I move it. But there is a real line for when things turn around, and it's when this gamma twiddle is 1. You can say what that intensity is. For 15 eV, that's pretty high intensity, and you're nowhere near it. So.
Okay, thanks. Now let's make 2 wave packets. Okay, and first, without infrared field. So I make one wave packet with an attosecond pulse, and then a little bit later, half a cycle later, I make another one with another attosecond pulse, identical. And what do I get on my detector? So it's very much like you have two optical pulse, and then you look at the spectrum. What you see is the spectrum of one pulse, which is modulated with interference. Okay, this is very much the same. Here you make 2 attosecond electron wave packets, and then you look in momentum space, and what you see is really the distribution of the momentum space distribution of 1, which is then modulated. And if you look at the structure of the fringes here, so you just add two amplitudes, and the structure depends on the phase difference between the two amplitudes. And if you look at this phase difference, you find, first of all, a pi factor, which is simply due from, it comes from the phase flip of consecutive attosecond pulse of pi, which I mentioned. And then there is a term which is just the energy absorbed divided by h bar times the time difference here. Okay, now you look where the fringes are maximum. This should be equal to a multiple of 2 pi. Then you find that the energy should be an odd number of h bar omega. This is the harmonics. We are happy. Now the structure, obviously the energy includes the kinetic energy, and obviously this should be circles centered on the origin here. Now let's add an infrared field, and first I am adding an infrared field such that the attosecond pulse coincide with the zero of the vector potential. There is no momentum transfer. Okay, you just add the two distribution like that. Then what do you see? Well, if you look again at this sum here and look where the fringes are, as you can see here, you get circles, but this time they are not centered on the center of the momentum distribution. They are off-centered. They are off-centered because there is an additional term here which comes from the difference in dynamics of in the field of the two attosecond wave packets that you create. And this term is proportional actually to the electric field. Now let's look at the other case where now the attosecond pulse coincide with the extrema of the vector potential. Then you move one attosecond electron wave packet upwards. You move the other one downwards. They interfere like that. What do you get? Well, you get interference where the two distributions overlap in the side region here and slightly here in this example. And if you look again at the structure here, first of all, the terms which depends on the field cancel out. There is no difference here in the dynamics in the field. But now this time, you can see it here, what you make overlap here really is two different momenta of your initial momentum distribution. You make overlap a point here in the upper part of your initial momentum distribution with a point on the lower part of your initial distribution, so that you get a phase difference here, which is really which comes from the phase of this dipole moment here, taken at two different points in momentum space. And what you can probe here is really two different points in momentum space or your initial distribution, separated by this momentum shift due to the field. So you have EA in one direction and minus EA in the other direction. So you have two times EA. You can go a little bit further. This is an interferogram. You can try to analyze it. This is the structure of the interferogram. You can, by Fourier transform, you can recover the delta phi here. You get something like that with an interesting phase change here. And you can get rid of the rapidly varying phase, which comes from the energy term. And then you get here the structure that in this region there is a phase change of pi, whereas here there is no phase change. And this is maybe not surprising. I'm looking at the S to P transition in helium, and well, if you know a little bit of atomic physics, the corresponding wave function is antisymmetric. Oh, this is the total phase. And here I'm just removing the rapidly phase. So this is really the phase difference between the two wave packets. And okay, so you know that, well, this part is actually there is a sign change between the upper part of the distribution and the lower part, so that you expect indeed to have a phase jump of pi here, and here no phase pi. Now, how do we do that experimentally? Well, we have our attosecond pulse train synchronized with the infrared field here that we sent in the sensitive region of a velocity map imaging spectrometer that was brought to Lund from Mark's group. And we have also a atomic beam here sending argon atoms. The experiment was done in argon. So the electrons were collected by an electric field here and projected on microchannel plates. And and what we get is a two-dimensional projection. From that you can retrieve the three-dimensional momentum distribution, and what I'm showing is two-dimensional cut in this three-dimensional distribution that you see here. This is when you only have a train of attosecond pulse here, harmonics. What do we see? First, let's look at the case of no momentum share, so the two distribution like that. First of all, you have to realize that we go from two pulse to multiple pulse. Okay, this is a little bit Fabry-Perot effect or multiple slit effect. What do we expect? In the two pulse case, we have an off-centered circle upwards due to interference between pulse 1 and pulse 2. Now, if you have a train of attosecond pulse, you also have interference between pulse 2 and pulse 3. This leads to off-centered circles downwards this time. And then you have, of course, interference between the wave packet due to interaction with pulse 1 and pulse 3. And this leads to a concentric circle. This is simply energy conservation. So you have circles centered upwards, downwards, and then at the center. What do we see? We see something like that. This is the experimental results. This is the, at the center, this is a pure above threshold ionization. Just forget the center part here. Look at the outer part here, which shows beautiful interference structures. So here we see circles centered at the center of the distribution. We also see circles, I them help you here, centered upwards. And let's look at the other case where there is a momentum share. And again, you go from two pulse to multiple pulse. So you expect more interference structures and some kind of a Fabry-Perot effect. The line should be actually sharper. However, the interesting interference structure on the side here should remain, and indeed this is what we see. It's a little bit noisy, but you see this beautiful interference structure here on the sides. Now a little bit of atomic physics now. This is the experimental results, and here what I'm showing here is this interference structure on the side, on the px axis. And if you look at the peaks are they correspond to an absorption of even number of infrared photons. What does it mean? This is elementary algebra. This is the interference structure, pi plus this is the energy term, the phase difference. The experiment tells us that this is equal to, this should be equal to 2n pi. Experiment tells us that this is it corresponds to an even number of photons. You can do the algebra yourself. You find that delta phi should be equal to pi. What does it mean? Now argon, this is ionization from the 3p state to S or D continua. You can go from the m equals 0 state, and in that case what you expect, the final wave function is symmetric. So in that case you expect no phase difference between the upper part and the lower part. And now, if you go from m equal plus or minus state, in that case you expect a sign difference. So what these results tell us, this is maybe not so very much, is that what we see here in this region of the momentum distribution, where we see the strongest overlap and very clear interference structure, is that ionization is dominated by this transition. This is what we see. Now, this is a kind of proof of principle experiment. Of course, we want to do much better. We want to increase and vary the overlap. We want to use 2 pulses maybe instead of a train. We would like to use cross polarization to really be able to map out the phase much better. And now comes my question to you. Can we learn something useful with this technique? Is there something to learn? I'm really serious. Yes.
I only have a question back, but it's a rhetorical question, the way I certainly don't know the answer. You presumably are sensitive to continuum structure in this measurement because that plays a role in the cross sections, and so there will be in the momentum imprint in the wave packet the information about the continuum structure. Are there any signatures of that? I mean, I don't know the spectrum of argon in this region, and maybe there are no interesting structures, but you know, maybe are they picked up in the measurement if they're there?
The answer is no. No, we don't see anything like that. I don't think we have any resolution to see that. But yes, they should be structured.
Yeah, but they sort of induce phase shifts in the wave function, and it's phase shifts that I guess you're sensitive to. So even though maybe the amplitudes could be weak, you might be sensitive to those phase shifts. In that case, of course, then it becomes interesting because you've got some way to look at those states.
Yeah. Okay, let me continue. Because time is passing. This is just the movie we made. It's not very nice, but you see, this is where you have the largest momentum share distribution like that. Importantly, we were cutting the top of the distribution, so we miss a little bit the top of the distribution here, and this is where we see the strong interference structure on the side. And this is as you vary the delay between the infrared field. So this is half a cycle here. And this is where we have the circles most off center. So this is quite interesting because the momentum distribution, they follow the vector potential. Whereas these off-centered cycles that we see, they follow the electric field. This is very interesting. You see that the distribution here increase, momentum distribution, whereas the circles go down, following the electric field. Now, what happens if you only have 1 pulse per cycle? Life becomes much simpler. And this is a movie now that will be presented by Johan. Now, this time scale is a bit different. Now you have a full cycle here, and what you really see here is really this distribution moving upwards and downwards. This is what you can see here. Of course, you have interference because this is not one single attosecond pulse, but a train of attosecond pulse with 1 pulse per cycle. But you really see the distribution moving up, which means we are really sending electrons up. We are controlling the motion of the electron or down. Finally, I'd like to present some rather recent results about ionization dynamics of wave packets at an attosecond time scale. And the question we ask ourselves is, okay, we look at this process here where we ionize the atom with an XUV pulse in presence of an infrared field, and we look at the electron distribution. Does something happen to ionization? Do you think the ionization here depends on the infrared field? What do you think? No. Now, what happens is instead we excite the atom with actually an attosecond pulse, which is just below threshold. In that case, will the ionization be affected by the timing between the XUV pulse and the infrared pulse? It's actually close to there was a theoretical calculation, something very similar by Brabeck and Strinzier a few years ago. This is how we do it. We generate harmonics in xenon. So we have a wave packet centered at about 20 eV, and this is actually the spectral content of this of our attosecond pulse train. So it's really only 4 harmonics, and you see that if you ionize argon, then this spectrum is above the threshold, so we are in this situation. Whereas if you ionize helium with these pulses, then we are mostly, not quite, but mostly below threshold, so you are in this situation. And this is the pulse duration of the corresponding attosecond pulse of about 370 attoseconds. What do we see? This is ionization yield as a function of delay, and the red line here is the ionization ion, argon ion, and then you see that it does not depend on the timing between the attosecond pulse and the infrared laser. Fine. Now let's look at the helium plus ion yield. You see that it clearly oscillates as a function of the timing. First, there is an enhancement of the ionization compared to no infrared. Okay? There is a little bit of ionization without the infrared due to the 17th harmonic, which is above the threshold. But now when you add the infrared, there is a rather strong enhancement by a factor of 3 to 4 of the ionization yield. And then there is a clear attosecond modulation. This is twice per cycle of the ion yield. The solid line here, this is theoretical results done by Johan and Ken. And you see that they agree relatively well. The contrast is a little bit larger with the experiment, and these are calculations performed at different intensities. Intensity was 1.3, 10 to 13 watts per square centimeter in this experiment. When do we see the maxima? What do you think? Well, we actually see the maxima of the ionization when the potential barrier is actually lowest. Okay. So can we interpret that as simply the potential barrier being over the barrier ionization? Maybe, we don't know. According to our theorists, this is not that clear. This picture is changing as a function of intensity. It's rather complicated. What do we see when we look at electron? This is, I think, the most interesting part of that. So this is electron spectra in argon. So this is when we have our electron wave packet really above threshold. And you recognize things that I have shown before. Here we see that you get the highest energy electron when you get the highest momentum transfer from the field at the zero of the electric field. Okay. And this is the experiment, and this is the theory result. Using time-dependent Schrödinger equation calculation. Now, what happens when you use helium? Similar structure, not as many peaks, but a similar structure. There is a clear modulation of the electron yield as a function of timing. In this case, however, there is a shift, a very significant shift of the position where you get the highest energy electrons. There is a shift here. You get the maximum energy electron at pi over 3. So how can we understand that? Well, the only thing we can say is that, okay, now we create a wave packet. You do not create the wave packet in the continuum free from the Coulomb potential. You really create a wave packet which is still really in the Coulomb potential. So the dynamics of that wave packet in the field will be very, very different from the case where you put your wave packet in the continuum here, away from the Coulomb potential. So what you see here is really the signature of the influence of the Coulomb potential, and which leads to this time delay. Maybe this is a way to say that this is really this atomic phase that we see here. Now, I can ask the question, is this multiphoton or over the barrier ionization? I think you're too tired to answer anyway, so. Just to finish on that, we also look at the momentum distribution, and what we can say is that really the wave packet that we create below threshold are very different from the wave packet that we create above threshold. This is a one photon ionization process here, And you recognize here momentum distribution that I've shown you before. This momentum distribution here obtained in helium are very much like, much more like what we observed before with multiphoton ionization, with angular distribution really peaked along the polarization axis. So let me conclude by saying that I have done a little bit of Attosecond technology. What we have in Lund is really trains of below 200 attosecond pulses at different energies, and with 1 or 2 pulses per cycle synchronized with an infrared field. And I have presented some application, one about electron wave packet interferometry, towards control of electronic wave using 1 pulse per cycle, and also control of ionization dynamics if you use wave packet below threshold. Well, thank you for your attention.
I had 2 questions. One was, I was expecting you to say something about Rydberg period showing up in the dynamics. What's the principal quantum number you're exciting?
I mean, this is broad. This is, I don't know, 5 EV bandwidths wave packet.
So where
we
is it centered?
We are exciting many wave packets, maybe Rydberg states.
But where is the center? It's around n equals 3 or so? An EV or so below threshold?
The center is at 23 EV. So it's 2 or 3 EV below threshold, approximately. But 5 EV bandwidth, so it's
okay,
really broad.
So yeah, there's not just one Rydberg period.
And I think we do populate states. I mean, because we see ionization as when we delay very much the 2 field, we can still ionize. So we do populate many states, I believe.
Okay, my other question was, you have this simple picture of just adding the vector potential to figure out the change in the electron velocity. What I didn't understand about that is my picture of these pulses is that there's a focus, there's an inhomogeneity of the fields. Why can you just say it's this value and you don't have to think about all that?
I guess we have to think about that, but I don't know, this very simple picture works. That's the only thing I can say. It really works. Except, of course, in this helium result, but that's there are reasons for that.
So is it just not tightly focused or something, so that all the experimental action is at the peak intensity point?
One thing we do is that I think that the attosecond pulse are more focused than the infrared pulse. So electrons see a rather uniform intensity distribution.
Okay.
In most of the case. Yes.
In Kavli, we are also using train of attosecond pulses, and my question is, and I agree it's a perfect tool, and my question is, what is the dependence of this momentum distribution with respect to the carrier envelope phase? I don't know if you remember the result of the Milano group. You know, in this long trajectory with train of attosecond pulses, we observe some effect dependent on the carrier envelope phase, and I'm just wondering if you might have some blurring or some...
on the train?
On the train, yeah.
I think the structure of the train I don't think it depends so much on the carrier envelope phase of the driving pulse. And in particular, the carrier envelope phase of the attosecond pulse themselves really depends on the intensity and not on the carrier phase of the driving pulse. I'm not sure I answered that question. But so, I mean, all of this is without any phase stabilization.
Yeah, because in this pump probe scheme, you just remove the carrier envelope phase when you are doing superposition of your attosecond pulse plus the additional field.
I mean, this is done with very long driving pulses. So like the CEP has, I mean, not so important.
Yeah, but you are working within one optical cycle, so then the momenta transfer might shift a little bit. Or maybe I'm wrong.
No.
Other questions? Well, Anne asked a lot of questions of everyone, so I guess
Yeah.
we're a little tired and ready for coffee. So let's thank Anne again.